So in the previous video, we graphed a bunch of curves. This was one of them, the four-leaved rose. And in this video, we're going to show how to answer questions like, what is the area of one leaf enclosed by one leaf of the rose? So in other words, I want to find the area enclosed here. Okay? So how am I going to do that? Well, with polar coordinates, the area formula is the following. It's integral of 1/2 r squared d theta. And you may ask why, and I'll tell you very briefly why. If I take a sector of a circle of radius r and angle theta, the area of that sector is r squared theta. So if I'm going to look at a polar curve, I'm going to take infinitesimally small slices of theta. That's going to be my d theta. So that, if you would like to read more about that, it's in your book, but I'm not going to spend a whole lot of time with that because we're at the end of the semester, sort of. So I just want to get to the meat of the problem. So once you know that this is the formula, basically all you have to do is go ahead and use it. The difficulty with these pretty much is always tends to be finding the limits. This particular one is pretty straightforward because as we saw with this, when I start at theta equals 0, I'm here, right? And then at theta equals pi over 4, I was here. And then at theta equals pi over 2, I came back here. In other words, if I want to solve for when I'm hitting the origin, I'm going to go 0 equals sine 2 theta, right? 2 theta is going to be n pi. So theta is n pi over 2. And I'm going to start from 0, pi, 0, 1, 2, 3. So that's going to give me theta equals 0, and theta equals pi. So then, pi over 2, I'm sorry. So this is not too bad. It does help to take a look at how the curve is being drawn out, because that sort of helps you figure out what's going on. And then all I do is shove it in this formula. Sine of 2 theta squared d theta, and I go ahead and do that integral. Now, as you might recognize, because it is going to be something squared, you're going to have a lot of sine squared, cosine squared with these. There's going to be a lot of half angle formulas. So sine is 1 minus cosine, and the 2 goes to 4. So you might have to go back and take, because it's been a little bit of time since we did those, but hey, they're going to be on the final. So let's go ahead and make sure that we know how to do those. Trigonometric integrals. So I end up, okay, with 1/4 times pi over 2 minus 0 minus 0 minus 0. And there I have my answer. There's pi over 8. Oh, can we not see that? It's not quite right, pi. There we go, pi over 8. Okay, so that's one example which wasn't too bad. Okay, let me pick up another one which also isn't too bad. In the previous video, I had done one where I had graphed something where we had a circle and a cardioid. Let me see if we can do that one real quick. I believe it was the circle was r equals 1, and the cardioid was r equal 1/2. 1 plus cosine theta, right? So if I draw the cardioid first, if you remember this one, I'm starting here at theta equals 0, r equals 2. At theta equals pi over 4, we're going through 1, and then we get this heart-shaped business here. And then it goes like that. Okay, my cardioid looks too much like a heart. They're actually fairly fat, right? Anyway, something like that. And not a very good picture, but hey, that's what we have the other thing for. And then this is just the circle r equals 1. So we can look at various things. We can look at the area inside, the area outside. Let's do this part. Something over here. So this would be written something like the area outside the circle and inside the cardioid. Okay? As you can, it's kind of hard to see because I don't have colored chalk. Well, even the colored chalk I have doesn't appear well on this blackboard. But this was the circle here. So the circle intersects, and we have a piece on the outside and sort of some other junk on the inside. So if I'm looking for the area outside the circle, inside the cardioid, I want this bit. Overall, there's a nice trick for these that makes your life easier. And that's when at all possible, just try to do everything in the first quadrant and use symmetry. So what I'm going to do is I'm going to do 2 times this area. In this case, doesn't matter. Like we could have done it from minus pi over 2 to pi over 2. It would have been the same. But some cases it gets a little bit wacky, especially with those circles that are on the other side. I'm going to do another one of those for you guys. So whenever possible, if you can use symmetry and just keep it in the first quadrant, it's the easier way to go with these problems, for sure. And so what I'm going to do is I'm going to take the area from the cardioid and subtract it from the area from the circle. Now this is the thing, I want you guys to try to think about this in the form of polar coordinates. So what I'm really doing, this is my R, okay? And so I'm taking R to the cardioid, and I'm going to pull that all the way there, and then I'm going to take minus the R to the circle, which is just this bit, okay? So I can see that this is going to be my theta equals 0, and just from the graph, I can tell that I'm going from theta from 0 to pi over 2. But if I want, I can also go ahead and solve for this because you can see they intersect here. Okay? So if I want to solve for the intersection, and sometimes I do have to do that because like the next example, you won't be able to read it off the graph. So solve for the intersection. I just now let the 2 equations equal each other. 1 equals 1 plus cosine theta, right? So cosine theta equals 0. Theta equals pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay? So now, but I do have to be a little bit clever because this one corresponds to 3 pi over 2. This one corresponds to pi over 2, okay? If I did my integral, though, from pi over 2 to 3 pi over 2, I'd get this other part, which might also be a question, but that's not the question that we're trying to answer here. We're trying to answer this other bit, okay? So I can do 0 to pi over 2 multiplied by 2, or I can also think about this point as being negative pi over 2 instead of 3 pi over 2, so I can go from minus pi over 2 to pi over 2. Because I like to keep it all in the first quadrant, I'm going to do it that first way and do a then take area is 2 times the integral from 0 to pi over 2 of 1/2 times the outside curve. So we can do r outside squared minus 1/2 r inside squared d theta. And remember, I'm thinking of it as the outside minus the inside with respect to the r, so with respect to the radial direction. Okay? For the 2 and the 1/2 cancel, so I have 0 pi over 2. My outside curve was the cardioid, so this is 1 plus cosine theta squared, and my inside curve was just the circle. It happened to be of radius 1, so I don't have to worry about that, but okay. I'm going to write it up here now because I want to finish my integral for you guys, and there's not enough space. I'm going to work this out. Remember, it's going to be 1 plus 2 cosine theta plus cosine squared theta, and I have a minus 1. So those cancel out. This stuff now. Copy it. So again, this guy just comes here for a second. Here I've got a cosine squared. I have to use that half angle formula. Okay, now you just integrate this stuff. Derivative of sine is cosine. I've got theta over 2. And this is going to be sine of 2 theta. And then, of course, it's going to be over 4 because I have to remember this 1/2 multiplies that, and then I have to do U substitution there. Okay? But it doesn't matter here. You know, because it's all going to be 0. Okay. All right. Sine of pi over 2 is 1, right? So I've got 2, and then I've got pi over 2 here, so I've got pi over 4. Then I've got sine of pi, which is 0, and then I got 0, 0, 0. So that just turns out to be that.